745 Heavy is on the ILS, 25 left is low, window 180.
25 Heavy, Later, runway 25 left, correction line number 2, following Captain Heavy, Airbus 3, mile final.
Okay, number 2.
What's going on, guys? Flyby Simulations here, and welcome to the second episode in my Aircraft's Dissected series, wherein I delve into every switch and knob in the aircraft to give you guys an in-depth understanding of every system present in the ZIBO mod Boeing 737-800. In this episode, we're going to be taking a look at the aft overhead panel, as well as the central pedestal and the throttle quadrant, also known as the control stand in this aircraft, to understand how the pilots operate the engines, move the flaps and speed brakes, as well as understand the various ways in which pilots communicate with air traffic control. So, last thing I would like to say before starting is that if you haven't seen the first episode in this series, I highly encourage you to do so, as I cover all of these systems on the forward overhead panel in the aircraft, such as the aircraft's fuel, hydraulics, air conditioning systems, as well as the electrical systems in the aircraft. It'll greatly help you contextualize what you're about to learn in this episode, so yeah, go watch that if you haven't already. Additionally, I would also like to thank this person on screen who pointed out a few errors in my explanation in the previous video relating to the bleed air and pressurization systems in the aircraft. I will be leaving this comment in the description of all of the videos in this series so that you guys can obtain the correct information about these systems directly from the horse's mouth. That being said, let's jump into the flight deck and start this episode of Aircraft's Dissected. So, ladies and gentlemen, welcome to the aft overhead panel of the flight deck, which houses some important systems such as the Inertial Reference System, or the IRS, backup radio communication equipment, as well as different testing mechanisms to be able to check whether the aircraft properly responds to emergency situations such as stalls or overspeeding. As was the case in the first episode of the series, we will be using flows to get through these panels, so in the case of the aft overhead panel, we will be transitioning from left to right. So without further ado, let's jump into it. First up here, we have the ELT light, which stands for the Emergency Locator Transmitter. During an unlikely event of an emergency, such as an immersion in water or encountering high G-forces on impact with the ground, this system in the aircraft will send out an automatic distress signal, which can be detected by non-geostationary satellites to allow the aircraft to be found using various GPS systems. The switch is normally left to the armed position, and the light next to it comes on if such a signal has been emitted or if there is a fault with the system. Moving below, on the left here, we have the Leading Edge Devices Annunciator, which shows the position of the slats and flaps of the aircraft located on the leading edge of the wings. As the flaps move positions, these lights transition from being yellow, implying that the flaps are transitioning, to the green lights where they're fully extended. Underneath this panel is the PSEU light, which stands for Proximity Switch Electronic Unit. This system is responsible for making sure that the inputs made by the pilots when manipulating different moving parts in the aircraft actually have the desired results. For example, if the pilots decide to extend the flaps to the 5 position, it is this system that makes sure that the aircraft understands that command and properly executes it to extend the flaps to that position. So, on the top right here, we have the main display for the IRS system, which stands for the Inertial Reference System in the aircraft. Now, you may have heard me using that name a couple of times in this video series so far, the reason being that it's a very important system. The IRS system allows the aircraft to understand its own place with respect to its surroundings from a navigational perspective. This means that without the IRS system, the aircraft wouldn't know where it is, where it's headed, or what direction to fly. This is even more apparent when you see the central displays in front of the pilots when the IRS systems haven't been aligned. As you can see, there is no artificial horizon, no map screen, basically nothing that the pilots can use navigationally to be able to help fly the aircraft. Additionally, the IRS, among other things, also provides the pitch, roll, and yaw parameters of the aircraft at any time. So, coming over to this display, what you see on here can be manipulated by this knob over here, which allows you to gain a lot of information about the aircraft at any point in time. Switching it to this track/ground speed mode allows you to see the track the aircraft is flying as well as the ground speed of the aircraft. Switching it to PPOS allows pilots to see their present position through these coordinates up here. Note that these coordinates are in the degrees and minutes format, with latitude first and longitude second. So currently, when parked at gate Delta 5 at San Francisco International Airport, this display reads 37 degrees 37 minutes north and 122 degrees 22.8 minutes west. Switching the knob to wind shows the wind speed on the left and the wind direction on the right. Switching it to heading/status displays the aircraft's current heading on the left and the system status alerts on the right. This smaller knob here simply adjusts the brightness of the display. This keypad on the right allows the pilots to manually type the present position of the aircraft in order to assist a malfunctioning IRS system to get calibrated properly. This little knob here allows the pilots to switch between the left and right IRS systems in the aircraft. Of course, there are two of these systems because, as mentioned in the previous video, all important systems in this aircraft have another redundant or backup system in case of any faults or emergencies. Alright, so below the IRS display unit, we have the IRS mode selector unit, which allows pilots to be able to automatically align the IRS systems during the preliminary pre-flight procedure. Right off the bat, this GPS light here illuminates when there is a problem with the GPS system in the aircraft, thereby preventing the IRS units from obtaining the present position of the aircraft. Underneath this light are a pair of 4 lights, 4 for each IRS system. This first align light comes on when the IRS systems are in the process of aligning and obtaining their present position as well as their magnetic heading. This on DC light signifies that the IRS system is drawing direct current from the main battery units of the aircraft. This light normally comes on when the pilots switch this knob to the nav mode to align the IRS units and then extinguishes when it begins its alignment procedure. Coming underneath, this fault light simply signifies a fault with that specific IRS system. On the right, this DC fail light comes on if the IRS systems are unable to draw direct current to be operational. As for this knob below, we'll talk about this in the electrical power up procedure video, where we will start these aircraft from a cold and dark state and do a full flight with it. Moving further right here, we have this service interphone switch, which allows the pilots to communicate with ground personnel who have headsets connected to the aircraft. Moving below, this dome light switch allows the pilots to switch on this light, which illuminates the entire cockpit. The switch has 3 positions, which allows the pilots to switch between turning the light to be dim, bright, or completely off. Alright, so moving towards the right of the aft overhead panel, the first panel up here is the audio control panel, where pilots can change the overall configuration of the audio systems within the aircraft. Now, just a couple of things I needed to say before starting on this panel. Firstly, every switch with these little in-op stickers above them means that the system in question is inoperative. Airlines often do this when they order the aircraft from Boeing and don't wish to pay for another unnecessary system to be added into their aircrafts. However, since the cockpit configuration doesn't change, the buttons for those systems still exist, and hence, airlines put these little in-op stickers to highlight that those switches don't necessarily do anything. The next thing I wanted to say was, although the ZIBO mod is an amazing and faithful recreation of the 737-800 in X-Plane 11, it still doesn't simulate every single system in the aircraft. For example, these bottom row of knobs and switches here are not clickable and are therefore not simulated in this aircraft in any way. Therefore, my plan for switches like these throughout the aircraft is to still explain their function, but not to go into too much detail, as this way you know what the system does on the real aircraft, but don't need to learn too much as you won't be needing it on the ZIBO mod anyway. Sounds fair? Alright. So, to start off with, these top row of switches here all pertain to different radios the pilots can choose to transmit on. Starting off on the left here, we have 3 VHF radios, which stand for Very High Frequency Radios. These are the frequencies over which air traffic control communications happen all the time. Moving to the right, these 2 switches are the HF or High Frequency Radios. Unfortunately, these are unclickable and are therefore not simulated in the ZIBO mod. Moving to the side, we have the FLT or Flight Interphone systems that pilots can use to communicate with flight attendants in the back of the plane. The SVC switch is the service interphone system for pilots to communicate with the ground crews such as pushback drivers and such, and this PA switch obviously stands for passenger announcement, allowing pilots to talk over radio chatter and give public addresses to the passengers in the back. Coming down, these buttons allow the pilots to choose which radio communication channels they receive audio from. The buttons in this row pertain to the same audio channels as the row above, with these ones used to receive VHF frequency audio, these 2 used for HF frequency audio, and these ones for the flight interphone, the service interphone, and the PA system. However, the ZIBO mod only simulates these first 2 VHF buttons you see on the screen right now. Anyway, to listen on a particular channel, simply push the button and the button will light up. You can then spin the button around to adjust the volume of the incoming audio. Now, a note on transmission and reception of radio communications. Selecting a button to transmit on will automatically also allow pilots to receive audio from that source. For example, if I simply select VHF1 as my audio transmission source, then I will automatically also receive audio on VHF1. However, if I also select this VHF 2 knob, I will transmit only on VHF 1, but I will receive audio from both VHF 1 as well as VHF 2 sources. Just thought I'd let you guys know that. Coming underneath, this row of switches pertains to the navigational radios in the aircraft. Now, I must preface this by saying that my knowledge of navigational radios is quite limited, but I will tell you guys the basics of what I found out from my research. So, if you guys have never flown in a general aviation aircraft and have no prior experience with aviation in general, then it's important for you to understand that not all frequencies are used for voice communications. Some radio frequencies can also be used to allow an aircraft's navigation systems to synchronize with different navigational beacons littered all over the world, which allow the aircraft to perform complex visual approaches as well as perform perfect auto-land procedures using the ILS or instrument landing system during difficult weather conditions such as dense fog. However, along with communicating effortlessly with the complex navigational systems present in these modern airliners, these navigational beacons also emit different Morse code identifiers to allow pilots to listen to them and tune in various different courses, headings, and tracks to be able to fly an approach when the automatic navigation system doesn't work as intended. Therefore, these first two switches here allow pilots to listen to the two primary navigation radios. These two switches obviously are inoperative, and this marker switch I'm assuming relates to the approach marker audio. The speaker switch allows the pilots to redirect the navigation audio from one of these systems to the loudspeakers in the aircraft. However, this switch is also not simulated in the ZIBO 737. Coming down here, none of these switches are simulated in the aircraft. However, as mentioned before, I'll just go through some of them to give you guys a brief idea. Starting off with this switch, it is simply a push-to-talk switch. Push the switch up to talk over a radio to an external radio station, and push the switch down to talk over the intercom to an external radio station. This next knob here is a filter switch, which, when switched to the left, only lets in voice audio from radio chatter, and when switched to the right, only lets in the Morse code identifiers being emitted by navigational aids and beacons. And finally, it lets in both when switched to the middle both position. Finally, this last switch lets the pilot switch between operating the radios in the normal or alternate modes. Okay, so coming down, we have an engine display panel which displays some important engine-related information, as expected. These first two reverse lights light up when the thrust reversers in the aircraft experience a fault. Underneath this are two switches labeled EEC, which stand for Engine Electronic Control. The purpose of these switches is to automatically regulate the engines and have them operate at optimal parameters. These two engine control lights on either side illuminate when there is a fault with the EEC system. Under here is the oxygen indicator panel. Now, if you guys don't know, the oxygen masks that deploy for passengers are very different from those used by pilots during an emergency. The pilot's masks, as you can see on screen right now, are very specialized so as to allow them to breathe safely as well as operate the aircraft in the best way possible. Hence, the oxygen supply for the pilots is dedicated and is separated from the oxygen canisters present above the passenger seats that supply oxygen for the crew and passengers. The first gauge here, therefore, displays how much dedicated oxygen is available for the pilots to breathe in their specialized oxygen masks. This pass oxygen switch on the right is there to enable the drop of oxygen masks for the passengers and flight crew. When in the normal position, the automatic pressure systems will automatically deploy the masks in the event of a cabin depressurization. However, the pilots can also turn on the system manually in case the automated systems experience a fault. This light simply indicates when the masks have been deployed. Under here, we have three landing gear lights, which represent the position of the main undercarriage of the aircraft. When green, the landing gear are locked and down. When the lights are not illuminated, the landing gear is retracted and safely stowed within the wheel well of the aircraft. Next up, we have the flight data recorder switch, which, as the name implies, records different aircraft parameters every time the aircraft is in flight or when the aircraft is on the ground and has at least one engine running. The light beside it simply shows that the data recorder is inactive, off, or has a fault within it. To the right of the flight data recorder, we simply have two warning test systems. The first is the overspeed warning test, which sounds a simple noise in the cockpit to alert the pilots that the aircraft is overspeeding, like so. This second test system is a stall warning test, which, along with producing a noise in the cockpit, also arms a vibrating stick shaker within the yoke of both the captain and the first officer's yokes, to provide tactile feedback that the aircraft is in imminent danger of stalling. There are two buttons, and I don't really think I need to explain why. And that, ladies and gentlemen, brings us to the end of the exploration of the aft overhead panel. The rest of this video will focus on the main throttle quadrant in the aircraft, along with the central pedestal, which houses some of the main buttons, switches, and displays that pilots use to communicate with air traffic control. So, without further ado, let's start with this throttle quadrant, located in the middle of the captain's and first officer's seats. So, just as the previous panels, we will be taking the same approach of covering this part of the flight deck by going from left to right. So, on the very left, we have a trim wheel, which is mostly responsible for controlling the pitch of the aircraft. Now, if you come from flying a general aviation aircraft, this is basically just a manifestation of the overall trim system within those aircraft, as it helps pilots to relieve pressure on their sticks while flying the aircraft manually. You can imagine how pulling the yoke up and holding it in that position all the way throughout a climb can be painful for the pilots, so by trimming the aircraft up, they can hold the same pitch attitude with only minimal inputs on the yoke. As for the trim wheel itself, it can be moved using three different ways. One is by physically moving the wheel by putting your mouse over it in the sim, whereas in real life, pilots use a handle protruding from the side of the trim wheel to spin it when experiencing a hydraulic failure. The next way is by using these two convenient buttons located on both the pilot's yokes to trim the aircraft up or down. And the third and easiest way is when the autopilot systems are armed and they take control of the pitch modes in the aircraft to automatically spin the trim wheel during flight. This little strip next to the trim wheel is the trim indicator, which shows the numerical position of the pitch trim system. On regular flights, pilots manually set the trim to be somewhere in this green takeoff range just before takeoff, and the specific numerical value is decided by this FMC, or flight management computer, when it calculates the aircraft's climb performance based on the fuel weight, passenger weight, and the characteristics of the runway the aircraft is about to depart from. We'll be taking a more in-depth look at this in the taxi and takeoff episode of this series. Moving to this big white lever, this is the speed brake lever, which assists the aircraft in slowing down by extending these speed brakes over the wings. These markers on the side indicate the range by which pilots can extend the speed brakes during flight. When the aircraft is flying, the pilots can only extend the speed brakes until this flight detent mark. However, upon landing and when on the ground, the speed brakes can be extended all the way to the back, providing maximum aerodynamic braking action to assist the aircraft in slowing down. Note that extending the speed brakes mid-flight must be done manually, but this is not the case when the aircraft lands, as the speed brakes can simply be set to this arm position, which will automatically deploy the speed brakes when the pressure sensors within the back landing gear detect contact with the ground. Additionally, arming the speed brakes also illuminates this green light in front of the pilots to alert them that the brakes have been armed for deployment when the wheels touch the ground. Alright, so coming to the center here, I'm sure you all know what these two are, but for those absolute beginners out there, these are the main throttles, which control engine power and thrust in the aircraft. There are two, one for each engine of course, but pilots normally use both the throttle levers together to achieve the particular thrust setting that they want, unless there is a loss of thrust in an engine and the other engine needs to be used to compensate, or if one of the engines experiences a flat-out failure. Just like the trim wheel, there is more than one way in which these levers will move during flight. The first is obviously when pilots manually move the throttle levers, which, during normal flight operations, is usually only done during takeoff and during final approach towards a runway. The second way is by the auto throttle systems, which, along with the command autopilot systems, manage the aircraft's speed, heading, altitude, and vertical speed throughout the flight when the autopilot systems are functional. Now note that pulling the thrust levers all the way back doesn't shut the engines off. It simply runs them at an idle speed, where they still produce thrust, but just not enough to gain any real speed or momentum in a short period of time. Picture it as having your car turned on, the parking brake released, and a feather placed on the accelerator. Now, there are a couple of buttons on the throttle quadrant that allow pilots to turn on and off some important systems. Firstly, on the side of each throttle lever is this button, which disengages the auto throttle system. Pilots normally push this button when they are on final approach to the runway and are stabilized, meaning that the flaps and gear have been selected for landing and they want to take control of the thrust levers to manually land the aircraft. Additionally, these two switches in front of the thrust levers arms the TOGA mode, which stands for Takeoff and Go Around Thrust, which is a pre-programmed thrust setting in the flight management computer that instantly provides high thrust during the takeoff roll as well as during an aborted landing sequence, also known as the go-around. In front of these thrust levers, you have these two thrust reverser levers, which can only be activated when the main thrust levers are in their idle position. As you can see on screen here, the thrust reversers open these doors on the outside of the main structure of the engine to let the air in from the sides and being pushed forward from the front. What essentially happens is that the engine, instead of applying a force backward and accelerating forward, applies a force forward and therefore instead of accelerating begins decelerating, hence the name thrust reversers. This allows the aircraft to decelerate faster and, more importantly, takes some of the responsibility off of the brakes in the landing gear, which can get really hot if relied upon for the entire deceleration process. When these levers are simply lifted, the engines run at idle speed and therefore provide idle reverse thrust. However, pilots can manually pull these levers back to increase the deceleration by running the engines at a higher setting. If you've ever wondered why, before touchdown, the aircraft goes extremely quiet and then just after touchdown, it sounds like the engines are being spooled up again, it's because pilots turn the engines to their idle speed just before touchdown, and right after the back wheels make contact with the ground, they arm the thrust reversers, thereby accelerating the engines to a higher speed. Okay, so coming to the right, we have the main flap lever, which the pilots use to extend or retract the flaps depending on the phase of flight. These numbers on the side of the flap lever denote the angle that the flaps are extended at with respect to a horizontal wing in degrees. For example, extending the flap all the way to this 30 detent extends the flaps at an angle of 30 degrees from the horizontal, as you can see here. To move the flap, simply lift the lever and place it in any one of these detents besides these numbers. Additionally, any flap setting will also be displayed in this analog gauge in front of the pilot situated right next to the landing gear lever. On the right of the flap lever, you simply have another trim wheel which is identical to the one we just explored next to the captain's seat. So, coming behind the main throttle quadrant, we have some important flight systems as well as a few important emergency systems. Starting at the top left, we have this parking brake lever, which works identically to the park brake in a car. Pulling this lever up engages the rubberized brakes in the wheels of the aircraft, preventing the plane from moving around when on the ground. As you can see, it also illuminates this big, obvious red light to signify when it's on. In the middle here, we have these two fuel, ignition, and cutoff levers. Now you might remember from episode 1 that these are used to physically open the fuel lines in the aircraft to allow fuel to flow into the engines to be ignited for combustion and thrust. Watch the first episode in the series to know more. Next up, on the right, we have a couple of trim cutout switches, which prevent the pitch trim system in the aircraft from working. This first switch is a main electronic trim cutout switch, which prevents pilots from controlling the trim of the aircraft from the control yoke, as mentioned before. This other switch prevents the autopilot systems in the aircraft from operating the pitch trim system. You can also see that there are a couple of metal guards in front of each of these switches to prevent pilots from accidentally flipping these switches on or off. Finally, up here we have a little horn cutout button, which is mainly used for training purposes. Normally, when the aircraft is too close to the ground at low speeds without the landing gear extended or any of the flaps extended, the aircraft recognizes this as a danger, as it should, and sounds an alarm in the cockpit. However, if new pilot cadets are training in properly simulated conditions and are trying to perform no-flap landings or trying to fly low by the ground without the landing gear extended, then this button may be pressed to disable that alarm. Moving further back here, we have the overheat and fire protection panel, which becomes very important when, you guessed it, there are any overheating problems or any fires detected in major areas in the aircraft. To start off, these two buttons over here allow the pilots to select which fire detection loop they used to use to detect a possible fire in the aircraft. This aircraft has two dedicated fire detection loops, A and B, which work independently of each other. In the real aircraft, pilots will be able to switch between switching these loops for both sides to either A or B. However, this switch is not simulated on the Boeing 737 ZIBO mod and is hence always left to the both position. Moving below the switch, on the left side we have this test switch. Flicking it to the left simply allows pilots to test whether the engine and APU's fire detection units' fault and inoperative lights are working as intended. Flicking the same switch to the right tests these two engine overheat lights, this wheel well overheat lights, signifying a possible fire in the main landing gear compartment of the aircraft, as well as lights up these three large red lights in the middle. Additionally, a blaring alarm is also sounded to alert the pilots that there is an imminent danger on board, like so. So, let's come to the obvious feature of this panel, which are these three large switches in the middle. These switches are the engine isolation and fire extinguishing switches for the two engines as well as the APU in the middle. Now, unfortunately, I cannot simulate an engine fire for you in the ZIBO 737, so I will just give you a feel for it by pressing this test switch one more time. However, during a real fire, only the specific engine with the fire would light up. Assuming we have a fire in the right engine and it lights up along with an alarm, the pilots will pull this switch up first. What this does is that it isolates this engine from the rest of the aircraft, but physically disconnects the engine generators, the fuel lines, as well as the bleed air ducts connecting it to the onboard air conditioning system. More info on that in the first episode of this series. After pulling the switch up, pilots would then be able to twist the switch to the left or right to discharge the content of the fire extinguisher bottles located in the specific engine in an attempt to extinguish the fire. When twisted to the left, as we have done, it lights up this light over here to signify which extinguisher bottle has been used, and this green light is an additional visual cue for the pilots to see that the right engine's fire has been extinguished. Note that firstly, these buttons can only be pulled backward when the automatic fire detection loops in the aircraft actually detect a fire. This is to prevent the pilots from accidentally pulling these switches and disconnecting the entire engine from the aircraft, which can be very costly to the airline, as you can imagine. However, in an event that the onboard fire detection loops have experienced a fault or failure, there is a little button on the underside of each of these switches to manually override this function and for the pilots to be able to pull these switches back and extinguish the fire. Given enough time, you will see that the entire right side of the cockpit completely loses all power, as the main power generation source for the right side, namely the right engine, has been disconnected from the aircraft, as mentioned before. Now, if you're wondering, this APU fire extinguisher light is not clickable, though the alarm and indicators, as you saw before, are indeed simulated, sort of like gizmos. Finally, this test light over here simply allows the pilots to test whether the extinguisher indicator lights are working as intended. Alright, ladies and gentlemen, that finally brings us to the central pedestal of the aircraft, which, as mentioned before, houses some of the important radio, voice, and navigation systems in the aircraft. Now, as we did with the forward overhead panel in the first episode of the series, we will be covering this panel in a top-down fashion from left to right. However, as you might have noticed, some of the systems on the left side, namely the captain's side of this central pedestal, are identical to that of the first officer's side on the right side, with a few key differences. So then, let's get into it. So, starting off, on the top left here, we have the radio tuning panel, where pilots can tune in the pre-specified radio frequencies to be able to talk to air traffic control or even to other aircraft. The two most obvious features on this panel are these two displays, which show the specific frequency that has been selected by the pilots. This left display here shows the active frequency that has been currently tuned and is being used for voice communication. The one on the right shows the standby frequency, where pilots can tune in a radio frequency that they wish to quickly switch to. This normally occurs when air traffic control asks the pilots to switch from their frequency to another. For example, say the ground controller gives the pilots a frequency to switch to and asks them to contact the tower controller. The pilots would then put the tower controller's frequency in the standby display and press this little transfer button, which swaps the frequencies on the two displays, making the previously standby frequency now the active one and the vice versa. Now, as you saw me doing just now, this knob over here can be used to change the standby frequency. Use this larger knob over here to change the numbers before the decimal point, and this smaller knob to change the numbers after the decimal point. This panel off switch here, when pressed, would normally turn off these displays. However, it's not simulated in the ZIBO mod 737. Next up, down here, we have some radio selection switches. However, only these two VHF1 and VHF2 switches are currently simulated in the ZIBO 737. The basic premise behind these buttons is that there are multiple different radio systems in the aircraft that can all be independently used by the pilots. Notice how the numbers change in the display when I switch between VHF1 and VHF2. Now, in this particular configuration of the aircraft, there are two of these radio navigation panels, one on the captain's side, which is normally set to VHF1, and one on the first officer's side, which is normally set to VHF2. The reason for having multiple radio systems is simply redundancy and backup. Now notice what happens if I select VHF2 on the captain's side, which, as just mentioned, is normally used by the first officer. Adjusting the frequencies on the captain's side automatically changes the frequency on the first officer's side as well, as the same radio system is being used by both pilots. Additionally, in the real aircraft, a little light up here also lights up to alert pilots that they are using the same radio system instead of the two individual ones for each of them. However, this light isn't simulated in the ZIBO mod. Coming down here, we have this knob, which allows pilots to adjust the sensitivity of the high frequency or HF radios. This panel is indeed movable, but doesn't really do anything as the HF frequency buttons themselves are inoperative in the ZIBO 737. Coming underneath, we have the Navigational Radio Tuning Panel, which is similar to the Communication Radio Tuning Panel, but instead allows pilots to tune in the navigational frequencies of certain VOR stations and other nav beacons on the ground to fly complex visual approaches, as well as to use the ILS or Instrument Landing System to align both horizontally and vertically with a runway for landing, as mentioned before. Now, if you don't know what an ILS approach is or what VOR means, I'm planning to cover all of these terms in another series, where we take an in-depth look at how to fly different approaches and land in extremely difficult airports such as Innsbruck in Austria or Faro in Portugal. However, for now, a simple explanation will suffice. Just like the communication radio panels, there are two navigation radio systems in the aircraft, one on the captain's side and the other on the first officer's side. You can again use the larger knob to adjust the numbers before the decimal place and the smaller knob to adjust the numbers after the decimal place in the standby display. Additionally, you may press this transfer switch to swap the standby and active frequencies. Now, just another note. If you're wondering where to find these navigational frequencies that we're talking about, they're normally published on aerodrome approach charts that all pilots have access to. For example, this here is the ILS approach frequency for runway 28 right at San Francisco. Pilots would normally tune this frequency into this panel before landing, along with the specific course of this runway on the MCP panel, which we will take a look at in the next video, to be able to perform an ILS landing on runway 28 right in San Francisco. Don't worry, if it sounds complicated now, it won't be so hard when we actually fly this aircraft from point A to B, and you'll see exactly what I mean when you see it for yourself. This test button simply allows the pilots to see if the VOR and ILS indicators are working properly on the navigational display or ND in the aircraft. However, this button is also not simulated in the ZIBO 737. Alright, so coming further underneath, we have the ADF panel, which stands for the Automatic Direction Finder. Now again, I must reiterate that my knowledge about navigational radio systems in the aircraft is quite limited, but from my research, the Automatic Direction Finder uses multiple different radio beacons on the ground that emit Morse code identifiers to find certain navigational information such as approach courses, bearings, and headings. So on this panel again, we have these two knobs to adjust the standby frequency as well as this transfer switch to swap the two frequencies. Now we also have these other two knobs here. This mode selector switch here allows pilots to switch between the ADF mode and the ANT mode. Normally this switch is left to the ADF position, where the ADF system will send the navigational bearing to the navigational display in the aircraft. Switching this to the ANT mode provides better audio reception. However, most of the research and documentation online suggests that you won't get any bearing information on the nav display as you would if you leave the switch to the ADF position. This other switch here simply switches the ADF system display on and off, as you can see on screen here. Coming down to the last main panel on this side, we have the audio control panel, which is identical to the one we explored in detail in the Aft Overhead Panel just previously in this episode. So rewind the video to this point if you need another refresher. Again, like all of the above mentioned navigational radios, there are two of these systems, one on the captain's side and the other on the first officer's side. Alright, so that brings us to the central column on the central pedestal, where the first panel is the cargo fire control panel. Unfortunately, none of these switches on this panel, apart from this little test switch, are simulated in the ZIBO 737, but let me just give you guys a brief overview of what each system does anyway. The primary function of this panel is to identify and, when needed, extinguish any fires in the cargo compartments of the plane. Pressing this test button over here lights up the fire extinguisher test lights, the forward and aft cargo extinguisher bottle arm lights, as well as the extinguisher bottle discharge lights, as you can see on screen right now. These two switches in the middle, just like the engine and APU fire detection systems, allow the pilots to choose between fire detection loop A or B to detect a fire in the forward and aft cargo holds of the aircraft. Coming further below, we have the weather radar control panel in the aircraft. Note that this entire panel is not simulated within this aircraft, including all of these buttons and any indicator lights or switches. Hence, I don't feel that we should waste any time in delving into this panel, as we will never use this panel when operating the ZIBO Mod 737 aircraft. When ZIBO does add functionality to this panel, I'll be sure to come back to this panel and make another video highlighting the weather radar systems in the aircraft in detail. That being said, however, I will leave links to websites and other documentation down in the description if you wish to know more about the weather radar system within the 737-800. Additionally, I must also mention that though these specific weather radar settings cannot be adjusted in the aircraft, the ZIBO 737 does still have a fully fledged weather radar system that provides both weather as well as turbulence-related data on the main navigational display of the aircraft when selected on the main panels in front of the pilots in the flight deck. As mentioned before, we will be exploring these panels in the next episode in the series. Alright, so coming underneath, we have the transponder panel. Now, before we delve into the switches and knobs on this panel, let's first understand what a transponder is. A transponder is another radio device that sits in the aircraft which is responsible for sending different important aircraft parameters such as the aircraft's altitude, speed, and direction at any given time during flight to both air traffic control as well as other nearby aircraft. Now, most modern airliners today are fitted with a type of transponder called a Mode S or Mode Sierra transponder, which allows these sophisticated systems to automatically send this data to air traffic control as well as to prevent mid-air collisions between aircrafts using various traffic advisory anti-collision alarms and indicators present within these systems. We will explore this further when we get to their associated switches. Additionally, before every flight, when the pilots obtain clearance from air traffic control, they're normally assigned a unique 4-digit squawk code, which, when tuned into this display, allows air traffic control to identify the aircraft's call sign, its speed, altitude, and other aircraft parameters mentioned before. So, let's take a look at these switches now to understand what each of them do on this aircraft. This knob over here is the TCAS system, which stands for the Traffic Collision Avoidance System, which sounds little audible alarms in the cockpit when the transponders of two aircrafts detect that they're getting too close to each other, thereby breaching safety regulations. The knob itself allows pilots to switch between the different modes offered by the transponder. When switched to standby, the transponder system is running but not actively sending out any information to air traffic control or any other aircraft in the vicinity. Switching this knob to the test position starts an audible testing system within the transponder with some visual cues on the ND or navigation display like so.
Climb, clear of conflict, descend, 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 crossing, descend, descend, crossing, descend, descend, descend now, descend, descend now, increase climb, increase climb, increase descent. Increase descent. Maintain vertical speed. Maintain vertical speed. Crossing. Maintain. Monitor vertical speed. TCAS test. Pass.
Switching the knob to altitude off sends positional data to the air traffic control to show where the aircraft is on their radar displays, but doesn't display the aircraft's altitude. This is especially useful at busy airports, where pilots will be instructed to switch on their transponders but set the altitude off, as it's understood then that they are on the ground, but the air traffic control will still be able to monitor their position on the ground with respect to other aircraft. Switching the knob to altitude on sends positional data as well as altitude data to ATC. Finally, this TA mode stands for Traffic Advisory, which will sound an automated voice in the cockpit whenever the aircraft gets close to another aircraft. The voice will typically say traffic, traffic when the aircrafts are very close to each other and clear of conflict when the aircrafts have moved far enough away from each other. Finally, this TARA switch stands for the Traffic Advisory and Resolution Advisory, wherein the transponder and TCAS systems will do all of the aforementioned things, such as send positional as well as altitudinal data to ATC, as well as alert the pilots with an automated voice when an aircraft gets close, but it will also do one more thing. If the two aircrafts approaching one another both have Mode Sierra transponders, then both of these transponder systems will synchronize and provide a resolution advisory to both aircraft to prevent a collision. For example, if two aircraft are headed towards each other and are approximately a minute away from collision, the transponder systems on both aircrafts will synchronize and sound an automated voice in one aircraft telling it to climb, climb, and the other aircraft to descend, descend. The pilots will then take over manual control and either enter a steep climb or descent to avoid the chance of collision between the two aircraft. Hence, the transponder is always switched to the TARA mode before takeoff and only switched off when the aircraft has safely landed at the arrival airport. This switch over here is to switch between the two transponder systems in the aircraft, 1 and 2, now which is not simulated in the ZIBO 737. Coming to the middle here, we have these two knobs, which allow the pilots to enter in the special 4-digit code mentioned before into the transponder system. This outer knob on the left adjusts the thousandths place, the smaller knob on the left adjusts the hundredths place, this larger knob on the right adjusts the ones place, and the smaller knob on the right adjusts the tenths place. Finally, this button in the middle is the identification button, which is only pressed when the air traffic controller's screens are cluttered with aircraft and they wish to see who is speaking to them on the radios to direct them properly. In such a scenario, air traffic controllers would instruct the pilots to squawk ident, and when the pilots push this button, the little blip on the ATC's radar screens will flash for a few seconds, allowing them to locate the aircraft with respect to the plethora of other aircraft on their screens. Finally, on the bottom here is a strip of knobs and switches which adjust the lighting on the central pedestal, some trim control systems, as well as a flight deck door locking mechanism switch. Starting from the very left, this first knob controls the floodlights that illuminate from just behind the forward overhead panel onto the central pedestal. This next knob here simply adjusts the backlighting of the various switches, knobs, and displays on the center pedestal specifically. Coming to the right, we have some more trim systems, which help adjust aileron and rudder trim systems in the aircraft. Now, just like the pitch trim system we explored earlier, these trim systems control the roll and yaw characteristics of the aircraft, but are normally left in their normal zero position, wherein the controls are neither veering to the left or to the right and are perfectly straight. However, in the case of an emergency, such as an engine failure, asymmetrical thrust gets produced, as the working engine slowly turns the aircraft in the other direction. In such a case, pilots can align the rudder and ailerons to constantly be facing in a particular direction to zero this rolling and yawing motion out, and for the aircraft to fly straight as planned. The stabilizer trim switch is again related to the pitch trim system, but it's not simulated in the ZIBO 737. Finally, this button on the right manages the locking mechanism of the flight deck door. Leaving it to auto allows the automatic systems in the aircraft to manage the locking mechanism. Flicking the switch to unlocked obviously unlocks the door for just a few seconds, kind of like an electronic magnetic door. Finally, flicking the switch to deny obviously denies access to the flight deck. So that, ladies and gentlemen, brings us to the end of this episode of Aircrafts Dissected. If you've stuck around so far, congratulations! You now have a sound understanding of important navigational systems in the aircraft such as the IRS, as well as the different means by which aircrafts can communicate with air traffic control. Additionally, you've also learned how to operate the main thrust levers, speed brakes, flaps, and some other aerodynamic controls within the aircraft and the different phases of flight they're used in. Now, I must also mention that all of the documentation and websites I used to research for this video are linked down below in the description, including a written text version of this entire video if you prefer to read those and understand more about this aircraft. That being said, the next episode in this series will focus on the central panels right in front of the pilots, which includes the primary flight display, the navigation display, as well as some knobs and switches relating to the autopilot systems within the aircraft. If you guys enjoyed the video, make sure to fly by the comment section and let me know if there's any questions you'd like me to answer for you. Make sure to perform a full stop landing at the like button and the subscribe button if you enjoyed the content, and press the bell icon for future notifications from this channel. And as usual, thanks for flying by.